Hello dear students, welcome back to my YouTube channel. So we have something. One second. Am I audible and visible to all of you? Am I audible and visible to all of you? Okay. So let's start today's lecture. One second. One second, beta. Okay, so let's start the class. Let's start the class. One second, beta. Okay, so the last class we had a discussion on the topics, right? Motion of the charged particles in electric field, and we had some discussion on uh, basically what was the topic? Electric field lines. So in this particular class, so we will be discussing some numericals, then some graphical analysis of electric field, then we will discuss electric flux and Gauss's law. Okay. Okay. So let's start the numerical. So we had first numerical of today's class, and that is we have a particle. Okay. A charged drop is suspended in air in uniform electric field if direction of electric field is reversed. Then find acceleration of drop. Acceleration of okay. So let us solve the numerical. So we have what? We have a charged particle. We have a charged particle with some charge q and some mass f. and some mass m. Okay, so we know that the gravity will act downwards. So I will write mg, which is weight, it will act downwards. So if it is a positive, let us suppose it is a positive. Okay, so I will just place here a electric field in this way. Due to this particular electric field, the particle will feel a force in this particular way. That is electric force. Electric force. Okay. So, but here is a condition. It is suspended in air. Suspended means it is hanging in air. Now, it is not going downwards or upwards. It is hanging. So, basically, if the particle is hanging, so the forces must be balanced. So, can I write here my force, which is Fe, it should be equals to mg. Okay. So what is electric force Fe? So I can write electric force is charge into electric field is equals to mg. First equation. Now second here we have the point. Now if the direction of electric field is now reversed. So look here. This is my charged particle with same charge q and mass m. Here my forces are mg acting downwards and my electric field is in this way. If my electric field is acting downward, that means my Fe, it should be always acting in the same direction of electric field. So can I write here F net, my net force on this particular particle would be Fe plus mg. What is F net? Is it mass into acceleration is equals to Fe plus mg? Okay. So here Fe is equals to mg. I can write here Ma is equals to mg plus mg. Look, we can just cut out this m. So A equals to 2g. So the acceleration of this particular numerical would be 2 times g. Okay. This was an easy numerical, no? You can find the numerical, no? in each book, right? It's a very common example. Let us do one more example from the hanging of pendulum. Okay. So what we have a simple pendulum. We have a simple pendulum. Simple pendulum. So if we have a pendulum like this, it is hanging in this particular manner. Okay, bob with mass m, length of this string is L. In first case, there is no electric field. So simple pendulum, we have a mass is hanging in pendulum case. So what we can write? The time period of this particular pendulum will be equal to T equals to 2 pi under root of length of string divided by the gravity which is acting on it. Okay. Now let us apply some electric field. Let us apply some electric field. Mass m. Mass m, right? Let us apply some electric field in this particular way. Suppose length is L of this pendulum. So what I will write now, no? Look, mg will act downwards. Force also will act downwards. Fe, electric force. So I can write my net force will be equals to mg plus Fe. Mg plus Fe. So F net equals to mass into acceleration is equals to mg plus Fe. Fe is what? Electric force. Done. So look, I can write Ma is equals to mg and Fe is equals to QE. So I can write here, I will take m common from right side. I can write m here. It will become g plus qe divided by m. M cancel out. My acceleration came out to be, it is g plus qe divided by m. Okay. So this is equals to what? G effective acceleration. I guess there is some network issue. Let me check. That is good. Okay. So we got here net acceleration. That means if we have any pendulum in an electric field, so it is effective gravitational acceleration due to gravity will be changed, right? So what I can write now? Now look, I can write now t dash equals to 2 pi under root of length will be same L divided by G effective. I can write like this. Okay, so 2 pi under root of L. Instead of G effective, I will write here G plus QE divided by M. So it simply indicates that if we have any pendulum without electric field, its time period will be different if we are applying some electric field here. Done? Hmm? Easy? So let us change the whole scenario now. In this particular case, we had applied electric field in vertical direction. Now let us put an electric field in horizontal way. Then we can just check out what will be the effect on the time period. Okay. Look how we can do it. Okay. Look now. If we have my pendulum in this way. If we have my pendulum in this way with mass m, okay, and length is L. Now let us suppose we are applying electric force in this way. It's my electric force. So this particular bob will face an electric force Fe, which is equals to Q times E in this way. So one force is in the right side direction and one will be mg, which will be the downwards. So look, on the single body we have two forces. So what will be the net force? The net force according to my vector, it would be in this way. So net force will be equals to under root of Fe square plus mg square plus, look, angle is 90 now. Angle is 90 degrees, so we don't need to write anything about it, right? So look now, my answer would be equals to F net equals to, once again, so F net will be equals to under root of Fe. Fe means it is Q square E square plus M square G square. Okay, so F net. So what we can change from here now? So we got F net now. What is time period now? So time period will be equals to 2 pi under root of L by G effective. L by G effective. Okay. We can do one more thing now. Look, we can do one more thing here. Look, in this particular way, how to find my acceleration? Huh? If this is my Fe, so I can write it is ma equals to qe. So my acceleration would be equals to qe by m. This one. So this one, my F equals to mg. So ma equals to mg, cancel out. So acceleration equals to g. Second equation. 2g acting in two different directions perpendicular to each other. So my net acceleration, I can write it equals to under root of q square e square by m square plus g square. Okay, so I can write here 2 pi under root of L divided by q square e square by m square plus g square. So this is how we can just manipulate our numericals now based on our needs. So now, so we have now graphical analysis of electric field. What we have now? Graphical analysis. Hello, beta. What we have now? Graphical analysis. Graphs. Okay. So for electric field, I guess my electric field equation is equals to KQ divided by R square. KQ divided by R square. So we know that from this particular equation, my electric field is inversely proportional to the R square. So this equation clearly gives us idea how to draw a graph. How to draw a graph between electric field and the distance. It would be what? Hyperbola. So the graph would be here what? Hyperbola. Right here, this will be hyperbola. Then it would be hyperbola. Now, if you have any sort of doubts, now you can just ask me here. No, then I will just choose those doubts. If you are just saying me some sort of relevant doubt, I can just answer that thing. If you are just saying me some irrelevant, no, I'm not going to answer those things. Okay, so we have the graph like this. So if you want to make a graph of electric field, so it will be a hyperbola. It will be a hyperbola. Look now, we have different cases in these things. Okay, so case number first. What we have now? Case number first. Look here. One, if we have a charged particle, it's my plus charge particle at origin. It's my origin. I am going in a right direction or I will go in the left direction. This will be positive. This will be negative. This will be okay. So in a right direction from the origin, we have the positive. In the left side of the origin, we have the negative. Clear now? Look, my electric field will be in this way. It's my electric field. This will be my electric field. Done? Look now, beta, electric field will be also positive negative. Okay. If right side we have positive electric field, so I can call this one as a negative electric field. Now make a graph of it. Make a graph of it. Look, we'll make a graph for it. Now look, positive R, negative R, positive E, negative E. Look here, if we are going towards the positive R, this is R now. If we are going towards the positive R, we will get positive R and we will get positive E. Again, this is my first quadrant. Now, if I am going in negative R direction, I will get my negative E. I guess negative now. So I guess this is my this one. This is how you need to make a graph of it. Okay. So let us discuss now case number second. Let us discuss now case number second. Case number second. In the case number second, so what we have charged particle negative. It is minus Q at origin. No? Okay. This will be plus R minus R. My electric field would be in this way. This is my electric field. Why? Because negative charge is the direction of electric field towards the charged particle. It will be like this way. Make a graph for this one. Make a graph for second one. Now, how to make a graph for it? Look now. Look here. If this is positive R, negative R, positive E, negative E. If we have positive R, but we will be having negative E. No? Look, right direction. It will this this side we have that electric field towards the inner, it will be negative. So this will be what? Positive. Look, positive or negative E. I guess it is this one. Negative or positive E. I guess this one. This is how we can make a graph of it. No, very easy. Okay. Let us discuss some complicated cases. No? If we have two charged particles, positive, positive, then positive, negative, then negative, negative, how to make a graph for it? Look it up. We have case number third. Case number third. Look. This is my origin. We have a charged particle Q here. We have a charged particle Q here, and it is at the origin. This charged particle is at the origin. Done? From a particular distance here, we have a charged particle plus Q. Done? Also here, we have a charged particle plus Q. Let us make a graph for it. How to represent the whole scenario in graphical terms. Look now. How to make a graph of it? Look. Positive R, negative R, no? Negative E, positive E. Look, we will study this particular point. We will study this particular point. Look, my electric field, due to this plus Q, my electric field will be in this way. Look, positive, no? This is my electric field. Here, my electric field will be in this way. Same case here, electric field due to this one will be in this way. At this particular case, it will be in this way. Okay, look. If we talk about the direction, is here we have negative R. It is negative R, this will be positive R. Okay, so how to make a graph now? So if we talk about the left side, if we talk about the left side, this left side, okay, look, my E is negative. Now let's focus on this particular thing now. This case, this one. Now, look, E is negative. In this case, my E is a negative. Also, my R is negative. I guess negative means we have this quadrant. This quadrant. Now, let us talk about this one. Let's talk about this one. Electric field is positive. Okay. R is positive. I guess it represents this particular side. Okay. Now let us study this one now. Let us study this one now. Look. This R is positive, no? The R is positive here. But if we talk about E, if we talk about E here, what is E now in this case? E will be negative. E is negative. In the same way, if we talk about this particular case, this one here, no? Look, E. Sir, E is positive. But R, sir, R will be negative. Now, how to make a graph of it? How to make a graph of it? E positive, R negative. So, sir, it will go in this way. Look, it will go. One second. It will go in this way. This is my graph. This will be my. Look now, if we talk about this region, now, look, my E is negative by R is positive. If we talk about this region, my R is negative and my E will be positive. Done? Yes. Look, we have a plan now. I guess you have missed on my previous lecture. We have a plan up to the August or September. I will complete my whole 12. Then from my September to December or to January, I will complete the whole 11. This is how we will make this graphs. Let us talk about the graph case number 4. Let us talk about case number 4. And this is also from AIMS PYQ. This was asked back in AIMS. So what we have, one second. At origin here, we have a charged particle. Let's have a charged particle here. Plus Q. Let's suppose like this, okay? And this is plus R. This will be minus R. We have two charges, one here, one here. Charges are minus Q plus Q. Okay. Let us discuss now. Firstly, we will discuss the effect of the charged particle, then we will make a graph. Due to this negative Q, my electric field will be in this way. Now, look. This electric field is negative. This electric field will be positive. And R is positive in both cases. Electric field will be in this way. Electric field will be in this way. This electric field will be positive and this electric field will be negative. R is negative. R is negative. Look at how to make a graph of it, no? So I will just make a replica of it here. Look. It's my origin, no? One, this one and this one. Here we have plus Q charge particle here, plus Q. And this is basically a null point now. This is basically a null point. We have discussed what is null point, okay? So if we make a graph for this particular portion, E is negative, R is positive. E is negative, R is positive. I guess I will make a graph in this way. This particular portion done. We will talk about this one now. We will talk about this one now. Look, E is positive, but R is positive. Both are positive, no? I guess I can make it like this. Both positive. Let us talk about now this particular portion. This one. Look, E positive, R negative. E positive, R negative. Okay. This one now. Look, E negative, R negative. It is simple. This one. This is how we make the graph. Easy, no? Do you know? Look, in the previous case, now in the previous case here, in the previous case, if you zoom now, if you just look towards this particular portion, this one, look, this portion, this one, it is zero, no? The value is zero. Do you know why? Look, electric field here, this is rightwards, leftwards. So in this particular point, my E net will be zero. E net is zero. But if we talk about this particular portion, electric field is right direction. This is also right. So I will write here, my electric field net is not equals to zero. That's why it is uplifted. No, it is not zero. It is uplifted. So these are four cases that we need to draw in graphical representation of electric field. How to make the electric field graphs, okay? And these are more than enough. Let us talk about now force per unit length. Let's talk about now force per unit length. How to find force per unit length. Okay. If we have an infinite line. I guess we had done this case now. Previously we had done this case. We have two lines. Look here, what we have? We have two lines. Done. Both lines are infinite. Both lines are infinite. With charge density plus lambda, plus lambda. That means same linear charge densities. Now look, if the distance between these two lines given to be r, if the distance between these two lines is given to be r, my question to you is calculate force per unit length on second wire due to first. So look here. Let us take a small element here. No, let us take a small element here. Small. If the charge on this second one, this is first one and second one. If the charge on second one is Q, capital Q, I guess the charge on this small portion will be dq, and the length of this small will be dl. Okay. We know that electric field around an infinite line will be electric field. So electric field is equal to how much? 2k lambda by r. So this electric field due to what? 1. This electric field will apply or will exert a force on this one. So I can write force on second wire due to first wire will be equals to charge on second wire multiplied by electric field due to first wire. What is charge on second wire? We don't know now. So what I can write here, sir, we know that lambda is equals to charge per unit length. So charge is equals to lambda into length. It is 2. Let us suppose, right? So force on 2 due to first will be equals to lambda 2 into dl multiplied by it. If it is delta 1, I can write 2. One second. Okay. So I can write here charge on second wire, that is equals to how much? Lambda 2 into dl. Electric field is equals to 2k lambda 1 into by r. So my force on second wire due to first wire will be equals to 2k lambda 1 lambda 2 dl whole divided by the r. Okay, but we don't need to find the force now. We have to find force per unit length. If we need to calculate force per unit length, so I can write force on 2 due to 1 divided by dl. It becomes equal to k lambda 1 lambda 2 divided by r. Is what? Look, this sort of represent as force per unit length. Okay, this force per unit length. This is how you need to manipulate this numerical. Easy, no? This one is very easy. Okay, so let us do one more numerical, then we will start electric flux and Gauss's law. Okay, one last numerical. Look, we have a system, something like this. Look, we have a system. Okay, look, it's my system. Okay, here what we have, we have line plus lambda infinite. Okay, so my particle is initially here. Initially, but we know that this line will exert a force on this particle. It will go displaced by this, okay, with mass m and charge q. So we have to find out this theta. Thank you, beta ji. Thank you. Okay, so we have to find out this theta basically. Okay, how we can do it? If it is in equilibrium, okay, if this is string, so we know that there will be a tension T. Okay, so if this is theta, so this will be also theta. So I can write here that this will be T cos theta, and this will be how much? The T sin theta. Downwards, what we have m into g. In this direction, what we have force, electric force, and it is equal to charge into electric field. Done. If it is in this whole thing is in equilibrium now, so what I need to write? I will write T sin theta gets balanced by q times E. Okay, and T cos theta gets balanced by mg. Look now, divide the two, T cancel out, sin theta by cos theta is tan theta. It will be QE divided by mg. So my theta came out to be tan inverse QE by mg. Easy? Easy, no? Very easy. Easy? Okay. So let's start most important topic, electric flux. Electric flux. Okay, so in the class, so we will be discussing now what? Electric flux. Electric flux. So what defines electric flux? What defines electric flux? Okay, so before discussing the electric flux, we need to discuss something about the area. Before discussing electric flux, we need to discuss something about the area. So what we need to discuss about the area? So we have to discuss basically area is a vector quantity. So what we have here? We have here area. What we have here? Area. So we will treat area as a vector quantity. We will treat here area as a vector quantity. Okay, so we can find it is magnitude, no? But what about the direction? How to get it is direction? If my area is vector in this particular case, so how to get the direction of my area? So it is direction would be perpendicular. The direction of my area would be perpendicular to the surface. Perpendicular to the surface. Okay. Suppose if look now, if this is my area, if this is particular my area, okay, and we have to find out it is direction. So its direction will be either in this way. Now, look, it is perpendicular. Okay, my direction of unit vector of my area to the surface should be perpendicular, normal. The angle between them should be the normal. Then it represents what? Direction of my area. Then look here. Look here, no? You see? So now we will talk about now electric flux. Now we will discuss about the electric flux. Basically, electric flux, we will denote it with this phi letter, and it is electric flux. It is number of, it is what? Number of electric field lines. Number of electric field lines passing through. Electric field lines passing through surface. Passing through surface. But the surface should be placed normally. It should be placed normally in electric field. In electric field. Okay. So electric flux means it is number of electric field lines passing through surface placed normally. Normally means perpendicular in electric field. Okay. The meaning of this line, the meaning of this line is, look, if we have electric field, look, if these lines represent my electric field lines, these lines represent my electric field lines. Okay, now here we have an area. We have an area. My area is in this way. This is my area. This is my what? Area. Okay. So we know that the area is making some angle. Look, this area is making some angle theta. So if anything is making area the angle theta, so we have to resolve it. So one component will be in this way and one component will be in this way. You can clearly see from this particular figure in this way, this one, this one. No line passes. No electric field line passes. Okay, so I can discard it. There is no usage of this one. But look, but through this one, maximum line is passed. So it will be what? A cos theta. Yeah, we have to take this one into consideration. A cos theta, no A sin theta. You can see from no particular figure that no, there is no line passing through from the A sin theta. The no line passes. So what is theta here? Theta is angle between. Theta is angle between my electric field lines or electric field and my area vector. Done? Easy, no? So now how to define a phi for this case? So phi will be equals to electric field, it is going to be E, and my area is how much? A cos theta. So can I write now phi is equals to electric field is also a vector quantity, area is also a vector quantity, two vectors with cos theta, so I will place here dot product. So if we have dot product, that simply indicates it is a scalar quantity. So electric flux is a scalar quantity. Now if we talk about it is units, so electric field is how much? Sir, it would be Newton per coulomb and area is meter square. So I can write it Newton meter square per coulomb. It is what? Newton meter square per coulomb is the unit of my electric flux. Okay, one more unit. No? Newton per coulomb. I can change it. I can write it volt per meter into meter square. 1 meter cancel out. It is volt meter also. So we have two units. One is Newton coulomb per meter square and one is voltmeter. Two units to calculate it. Easy, no? Look here. So look, if we have uniform electric field, for uniform electric field to get my phi is different. For my non-uniform electric field to get my phi is different. So how to get my phi in two different scenarios? Okay. Look, phi. If we have for uniform electric field, for uniform electric field, and one more for non-uniform, electric field. I can write phi is equals to E dot A. But for this one, I can write integration of E dot A. So now we have two formulas, E dot A or integration of E dot A. One we can use for uniform electric field and one we can use for non-uniform electric field. Non-uniform electric field. Then my network is good. Easy now? Easy or very easy? Easy? Okay. So we are done with these things now. So let us do some numericals. Okay. Let's do some numericals to get a better understanding of it. Some good numericals. Look now. Some very good numericals. My electric field is given to us, that is, it is 2 I cap, it is minus 3 j cap and plus 4 k cap, and my area is given in this way, it is I cap plus j cap. Find phi. Find phi. How we need to proceed numericals like this? Okay, how we can proceed numericals now? Look, we have to firstly just see towards the E and A. E and A. Both are given to us in ijk coordinates. That means in vector forms. Okay. And you can see from here now, look, E is constant now. Look, ijk, there is no dependency now. If there is no dependency, so I can use the formula. Which formula, sir? I can use the electric flux is equals to E dot A. Simply this would be E dot A. So electric field is 2I cap minus 3j cap plus 4k cap dot A is equals to I cap plus j cap. Look, 2I into I, sir, it will be 2 only. Minus 3j into j, it will be minus 3. plus 4 into 0, it will be 0. So my phi will be equals to 2 minus 3, that means minus 1 Newton per coulomb, it is meter square. Okay, one more numerical, different style numerical now. Second one is, if my electric field is equals to simple 2I cap plus 3J cap minus K cap, and my area is given to me, that is 10 meters square, lies in XY plane, then calculate flux linked through the surface. Look, from this data now, what we conclude that, yeah, sir, electric field is given to us now, but what about the area? Look here, area is 10 meters square. Sir, magnitude is given to us. What about direction? It is XY plane. XY plane means, look, this is my X, this is my Y, this is my XY plane. Okay, and my area is lying in this way. Look, this is my area. Then this is my area. XY plane. Okay, now if we are just making anything on it, no, it will be how much? Z axis. That means K cap. So it is 10 meters square K cap now. Okay, 10 meters square K cap. Okay, so how to get it now? Sir, phi is equals to E dot A. It is E dot A. E is 2I cap plus 3J cap minus K cap dot. What is A? I guess A is equals to 10K cap. 2 into 0 is 0. 3 into 0 is 0. Minus K, there is minus 1 into plus 10. I guess my phi came out to be, it is minus 10 Newton meter square per coulomb. Done? Easy? Okay, third numerical. We need to be a little bit fast now to complete our syllabus. Now my third numerical. Third numerical, like, electric field is now given in this way. It is 10 Newton per coulomb. Area is equals to 5 centimeters square. And surface makes an angle. Surface makes an angle of 30 degree with field. Find flux. Look, to get my flux now. To get my flux, what I need phi equals to E dot A. E dot A. Or I can write EA cos theta. EA cos theta. And theta is between what? It is between E and A. Between E and A, no? Then look now. So what I can write, sir, phi is E. What is E? Sir, E is 10. What is A? It is in centimeter square, so I need to change this one into meter square. So I can write 5 into 10 to the power minus 4 meter square. 10 into 5 into 10 to the power minus 4. Then cos 30. No, this is not 30 now. You know why? If we have a surface like this, look. If we have a surface like this, okay, this is my electric field. This would be my area. So theta is this one, no? But it is not given to us. This one is given to us. This one. It is 30 degree. So what will be this one? Says 60 degree. So I need to write cos 60 degree. Okay. I can write 5 10 to power minus 4 plus 1. What is cos 60? It is 1 by 2. It is 2.5 10 to power minus 3. Okay. Or I can write 25 10 to power minus 4 Newton meter square per coulomb. Done. One more numerical. One more numerical. Okay. Electric field is equals to 10 Newton per coulomb. Area equals to 10 meter square. And theta is now given to us, that is 60 degree. How to get my answer? Simple. Phi equals to EA cos theta. E is 10, A is 10, cos 60. So cos 60 is 1 by 2. I guess my answer is 50 Newton meter square per coulomb. Done? Look now. One more. Let us learn something about the angles. If my surface is in this way, if this is my surface and my electric field is passing like this, my electric field is passing in this manner. Okay, it's my electric field. It's my electric field passing in this manner. Look now. If it is E, length of this square is L. Now, how to get my phi? Sir, phi is equals to EA cos theta. EA cos theta. But here now, if let us suppose, let us just turn it now in this way. So what we get now, look, it will be in this, it will looks like this now, look. So my electric field are going in this way. Okay, electric field. And my area vector will be like this. It's my area vector. Electric field. So angle is 90 degree. And cos 90 is 0. So which simply indicates that my phi in this case will be 0. My phi in this case will be 0. If I just change it now, there won't be any effect. If I change it, look. Look, if my electric field is going in this way now. Look here. Still in this case, my theta is 90 degree only. So I guess if I need to write phi is also 0. Why? Cos 90 is 0. That's why we will get it 0 now. Easy? So up to this particular portion we discussed some figures, but all these figures were belong to what? 2D objects. We had the rectangle, we have triangle, right? We have these surfaces now. All, if you can just check now, all these surfaces were 2D surfaces. Let us talk about 3D surfaces or closed surfaces. If we have any closed surface, if we have any closed surface, how to deal with closed surfaces? How to deal with now what? Closed surfaces. So we have half an hour time now. Okay, we'll finish the Gauss Law up to then now. Look, what we have here, we have a 3D objects, or you can write the heading as positive and negative flux. We have positive and negative flux. Negative flux. So these terms, positive and negative terms, these are only defined for our 3D objects. So these are defined for 3D objects. 3D objects. Or you can write, these are designed for what? Closed surfaces. If we have closed surfaces, so we have to take care of the direction of the flux. Okay. So if we have the closed surface, the direction of area vector is always perpendicular, like the 2D. Always perpendicular. Always perpendicular to surface. Perpendicular to surface, but outwards. But outwards. Sir, what is the meaning of outwards? Let us take an example. Simple example, we'll take it now. Look, if we have a 3D object like this, look. This is my 3D object. Okay, this is my cube. My cube. Look, my electric field lines will be like this now. Look, going in, okay, from this figure like this and coming out. Electric field lines. Look. So if we look, this is one surface, two surfaces, 3, 4, 5, and 6. Here, the area vector will be outwards and perpendicular. This face, area vector outwards and perpendicular. These area vectors won't be inside. No, this is wrong. Always outwards and perpendicular. These will be always outwards and perpendicular. Look, I guess this one is incoming. Flux is coming, lines are coming. These are outgoing flux. These are outgoing. Look, electric field is in this way, my area is in this way. I guess my angle is 180 degree. Look here. Area is in this way, electric field is in this way. I guess theta is 0 degree. Look, and cos 180. Cos 180 is equals to -1 and cos 0 equals to +1. What is flux here? So phi equals to EA cos 180 degree. Phi here equals to EA cos 0 degree. Phi incoming. EA. What is cos 180, sir? -1. Phi. EA. Cos 0 is +1. So phi incoming equals to -EA and phi outgoing is equals to +EA. Done? So based on this particular scenario, we have sign conventions. We have developed sign conventions. Sign convention. First sign convention is like that incoming flux is always negative. Incoming flux is always negative. Second point. outgoing flux is always positive. Third point, area is perpendicular and outwards. These are three sign conventions that we need to remember. We have to remember for 3D objects. We need to remember for what? 3D objects. There are a lot of ways now to discuss these things now. Look, now if somebody will ask you, what is phi net? If somebody will ask you what is phi net, so you can write, sir, phi net equals to phi in plus phi out plus phi out. So what is phi in? It is minus EA. What is phi out? It is plus EA. So phi net is equals to 0. It simply indicates that number of lines of electric field coming into the plane or into an object equals to number of lines outgoing. So incoming line is equals to outgoing line, so net flux is 0. Okay. So it is valid for any closed object. If my electric field is coming from outside, look, just remember this point. For any closed surface, for any 3D surface, if my electric field is coming from outwards, that means not for, we don't have any charge particle inside of it. No, if my electric field is coming outside, so my net flux will be 0 always. So my net flux will be always 0. Let us talk about the cylindrical case. Let's, we have cylinder also, no, 3D object. Look now, look beta. Okay, look, this particular figure represents a cylinder. Cylinder is a 3D object with one surface, this one surface, this one, and one is the curved one. Okay, now let us mark the area firstly. Area will be outwards, A1, and perpendicular. This one, area will be the outwards and perpendicular. This one, area 3, A3 will be outwards and perpendicular. Now my electric field lines are coming in this way. These lines represent electric field lines. This side, if it is phi 1, phi 2, phi 3. If we need to write phi net, I guess phi net is equals to phi 1 plus phi 2 plus phi 3. Look, in this phi 3, I guess angle is 90 degree now. Look, so phi 3 will be 0. It is 0. If the area is A, I guess same area will be here also A. So what is flux? Sir, EA cos 1, it is minus. This will be plus EA. Okay. So phi net is equals to phi 1 minus EA plus EA plus 0. So phi net will be equals to 0. One more proof for a closed surface. One more proof for a closed surface, that if the electric field lines are coming from outside, so it is net effective would be 0. Why? Because if 3 lines are coming, 3 lines will be leaving, no? So net is 0. If I am earning 100 rupees and I am just, my expenses are 100 rupees, so my saving is 0. Done? And this area means the area of projection. If you knew, look, there will be many cases now where you will find it difficult to find the area. If we have a cone, if we have a spherical, if we have a cylindrical, which area we want to use it? So it is a projectile area, projection of area. Projection of area means, look, what projection of area means? Now look better. Simple case. Let us talk about a simple case. Talk about the simple case. If we have a sphere, this sphere. If this is a sphere, what sphere? And my lines are in this way. These white straight lines represent electric field. Okay. These lines represent an electric field. Clear now? We know that. One thing we know that for sure that phi net is 0. We know that. We know it. But if in question you need to find out, the incoming flux, if you need to find out the incoming flux, so how to find the incoming flux? We know that, sir, incoming flux will equal to, it is minus EA only, right? Minus EA. But what is A? It is severe. How to find A now? Look, area means the maximum area. I guess if we draw a circle here now, look, this is the maximum area of our sphere. Yes, sir. So this will be the area. Okay, and it is a pi r square, simply pi r square. So I can write this as minus E into pi r square. Fine. Okay. So area means the area projection. I guess we had discussed the same thing in surface tension, no? Okay, how to get our excess pressure in case of excess pressure, we need to find out the area, that is area projection. If you have any doubt about it, you can just let me know. There's no issue. Okay. Now let us talk about the cylindrical one more thing. How to find for cylinder. Okay. One more time, let us talk about a cylinder. Look, if we have the cylinder in this way now, it is vertically now. Okay. My cylinder is in this position now. Done. And electric field lines are in this way. These lines represent electric field lines, and my radiuses are, length is L. Length is L. Okay. One thing that we know, that phi net flux is 0. Number of lines coming equals number of lines going out. Now, if we need to calculate a phi in, we know that it would be negative always. I can write negative EA. Negative E, we know now E. What is area? Sir, for area, one thing that you just told me now, one thing it would be this one. I will just cut it from here. Now look, I will just cut it from here. This portion. It is some sort of rectangle, right? It is, this length would be 2R and the height would be L. So what is area of this rectangle? Length into breadth. I can write length is how much? 2R into breadth is L. So my phi in is equals to minus 2RL times E. Look, that's why I just told you, this was the important one. Okay, this was the important one, no, beta? Easy. Okay, so I guess we had done now. We are done now with what? We are done now with electric flux. Now let us start Gauss's law. Let us start the last topic of today's class, that is Gauss's law. Gauss's law or Gauss's theorem. Okay, so first thing, the Gauss's law, it is only valid. It is only valid for closed surface. it is only valid for closed surfaces. First and foremost important, that is, it is valid for only closed surface, that is 3D surfaces. Second one, second point for Gauss's one, valid for fields, valid for fields following inverse square law, following inverse square law. That means we can apply Gauss's law in anywhere where we have the inverse square law. Okay, if you have the inverse square law, you can use the Gauss's theorem. That means if any force is depending on the distance in this way, this particular is inverse square law. Okay, so we can use the Gauss's law, just like in gravitation, force is equal to G m1 m2 by r square. Also there we can use the Gauss's law. Okay, so Gauss's law we can use now where we have the inverse square law following. Okay, now the main topic for Gauss's law is, it is statement, that means net flux is 1 by epsilon naught times the net flux from any 3D surface is equals to 1 by epsilon naught times of total charge enclosed. Total charge enclosed. Okay. Simple statement of Gauss's law. The state is that net flux of any 3D surface will be equals to the net charge enclosed in the 3D surface divided by epsilon naught. So I can write from here, sir, by Gauss's law, phi net flux will be equals to summation of charge divided by epsilon naught. Done. 1. I think I can write in different way also now. How, sir? Can I write now phi net is equals to integration of E dot ds? Yes, sir. I guess we had done this one now. If we have any non-uniform electric field, we know it now. Now merge these two. Look, left hand side same. So can I write now? Can I write the integration? This gola means closed integration of E dot ds. It will be equals to summation of charge divided by epsilon naught. This is the last one, right? That you need to remember. Most important one. This one. Q means enclosed charge. This is what? Enclosed charge. Electric field due to all charges. Due to all charges. All charges. These charges may be inside or outside. There is no issue. This electric field due to all charges, but right side the summation of Q is only due to the enclosed charges. Okay. Let us think about many things. No, look now. If we have a question, no, look, one surface, one more surface, one more surface. In first surface, we have a charge Q. Second surface, I have charge Q by 4, then 3Q by 4. Then I have minus Q by 4, then 5Q by 4. Done? So this one we have phi 1, phi 2, phi 3. Find the relation between these phi. Sir, we know that phi is equals to inside charge by epsilon naught. So what is inside charge? Sir, phi 1 is inside charge only Q by epsilon naught. This one, sir, phi 2 inside charge is Q by 4 plus 3q by 4 divided by epsilon naught. I guess it came out to be how much? Look, q by 4, 3q by 4 will be 4q by 4, 4 cancel out, it will be q by epsilon naught. This one, 5, 3, you can get it now. It will be 5q by 4 minus q by 4 divided by epsilon naught. I guess 5, 3 is also how much? Q by epsilon naught. So look, we had different, we had different sizes. Look, we have different sizes of 3D surface, but if the charge, if the summation of charge is same, if the summation of charge is same, so my flux will be same. So from this particular example, we conclude that my net flux does not depend on does not depend on shape. It does not depend on shape and size of surface, but that surface is Gaussian surface. Gaussian surface means the surface on which we are applying Gauss's law. Clear? So here now, if look, we are applying Gauss's law in these three cases. On this one and this one and this one, we are applying Gauss's law on these three cases, right? So these three surfaces are known as Gaussian surfaces. Okay, simple meaning Gaussian surfaces. One more point. Suppose if we have a surface like this, a 3D surface like this, Q1, Q2, and Q3. So can you tell me that phi net flux is due to which charge? I guess net flux is due to the internal charges, that is Q1 and Q2. But if you need to find out electric field, electric field will be due to Q1, due to Q2, due to Q3. Here now, that's how we are talking about this one. If we are talking about this particular area, okay, so flux will be only these two. Now look, flux will be these two, but here if you need to understand the electric field, this will also contribute for electric field, this will also contribute for electric field, and this will also contribute for electric field. Inside charge is only for net flux, but all the charges inside or outside, all these charges are what? Responsible for the electric field. Let us do one more numerical. Let us do some PYQs of IIT. IIT PYQ. If we have something like this, look. Okay. One second. Okay. Plus 2 coulomb is outside, minus 7 coulomb is inside. on this disc we have plus 6 coulomb. This rod is having plus 8 coulomb, but L by 4th is inside length. So we have to find out this is my Gaussian surface. This is my what? My Gaussian surface. Okay. So we have to find the flux, net flux. How to get it? Look, if 6 coulomb is on this one, that means 3 coulomb will be inside, 3 coulomb will be outside. So this will how much? Plus 3 coulomb. Look, on this L length we have 8 coulomb. That means one unit we have we have how much? We have basically it is L by 4. So can I write from this one? It would be 8 divided by 4 times, no? 4. Yeah. For L by 4, I can write 8 by 4. So this portion is having a charge of plus 8 by 4. So I can write 2 plus 2. It is plus 2 coulomb. Look inside. Now inside I have inside charge. Inside charge I have plus 3 coulomb, then minus 7 coulomb, then plus 3 coulomb, then plus 2 coulomb. So what is net? What is summation of Q? 3, 2, 3, 3. That it is 8 minus 7. It is 1 only, no? Am I correct? Once again, it is 7. It is 3. So no, there is only one 3, no? Only one 3. So I can write it equals to 3 minus 2 coulomb. Okay. So my phi net will be equals to minus 2 divided by epsilon naught. Done? Okay, I guess we are done with today's class. Okay. So from tomorrow, we will be discussing from Coulomb this Gauss law. Okay. So now we will discuss about how to draw cubical forms. Okay. On the corner, on the center, at the shaded portion. Okay. So these things we will be discussing in tomorrow's class. If you have any confusion or if you want to just tell me, and if you want to ask me anything, now you are most welcome for 5 to 4 minutes. Then I will just end the session. Okay, I guess you don't have any sort of doubts or you don't have anything that you want to ask me. So we will end the session here. Okay, rest thing we will discuss tomorrow. Bye, Beta. Bye.